The universe is awe-inspiring in its scale, mysteries, and beauty. Many people are drawn to astrophysics and astronomy for these very reasons. And today's guest, Skylar Grayson, is one of them.
Like, there is so much that is still unknown and a mystery. And I was really excited about the prospect of being a part of answering those questions.
And Skylar isn't just interested in understanding the universe. She wants to help other people understand it too.
Astronomy brings people together. It's a very, very popular science. And so there's a huge opportunity to help with science literacy, help build trust in science, help get people excited about science. That comes from caring about astronomy.
A PhD candidate in Arizona State University's School of Earth and Space Exploration, Skylar builds giant computer simulations to study how supermassive black holes shape entire galaxies. These digital universes run on supercomputers, track everything from gas to stars to dark matter, and help researchers piece together how galaxies evolve over billions of years. And outside the lab, she's built an audience online, explaining those same concepts in ways that people can actually understand, and clearing up some of the internet's favorite misconceptions about space. I'm Pete Zrioka, and this is Lab Coat Optional, the show where advanced research meets everyday curiosity. In this episode, we break down what black holes are and what they're not, how scientists can understand things that are billions of light years away, and why studying all this stuff matters to us here back on Earth. So stick around to hear all of that and more, including Skylar torture me with the mere mention of dark matter, which frightens and confuses me. Skylar, welcome to the show. I'm so excited to learn about some astrophysics with you today. I'm intimidated, but you're going to have to walk me through it.
It'll be great. It'll be fun.
Awesome. I had a question right off the bat that might seem kind of silly, but I do think it's important to differentiate these two things. You're an astrophysicist. What is the difference between that and an astronomer?
Yes. You know, sometimes these terms are used interchangeably, even by people in the community. But the more kind of appropriate way of thinking about it is astronomy is very focused on the where and the what, and astrophysics is more focused on the why. So astronomy is a lot of using telescopes to look at objects, map out where they are, what they're doing, see how they change, catalog things. And astrophysics is focused around using physics, which is why we bring that into the name, to understand why things are behaving the way they're behaving, where they came from, where they're going, how they're impacting the rest of their environment. And so it's more of interested in understanding the underlying mechanisms of how things work in the universe. And most of the field today is astrophysics.
Oh, okay.
There is a lot of cool astronomy that's being done in terms of big telescopes taking big surveys, but it's ultimately with the goal of doing astrophysics with that data, using it to answer big questions about how the universe functions. So
to apply a very rudimentary analogy to it, an astronomer is like a geographer or cartographer, like a map maker, and you are more like a geologist and trying to figure out why those landforms are where they are.
That's a great analogy.
Okay. Yeah. So you study supermassive black holes. What is a supermassive black hole, right, and how do they influence the space around them?
Yeah. So the basic idea behind a black hole is it's just an object that's very, very, very dense.
Okay.
And its gravity is so powerful that not even light can escape. So every object has some speed that you have to go in order to escape its gravity. And the deal with the black hole is because that speed is faster than the speed of light, and nothing in the universe can go faster than the speed of light, nothing can escape a black hole.
Okay.
There's a lot we don't understand about them in terms of the underlying physics, especially when we sort of pass that point of no return where no matter how fast you're going, you can't get out.
Event horizon.
Event horizon, that's
I love
exactly
that movie.
it. But what people don't realize is that there's a lot of stuff that's going on outside of the event horizon that's really, really important astrophysically speaking.
Okay.
So when you have a supermassive black hole, and we find these in the center of the galaxies, there are usually some stuff around them, normally a lot of gas. Sometimes there's stars or star clusters, but there's just material in the center of the galaxy that's getting slowly pulled in towards the black hole by its gravity, but isn't in there yet. And when there's a lot of that material and it's moving really, really quickly, it can get really, really hot, and that energy can escape because it's not in the black hole yet, so it can escape. And sometimes there's so much energy that it can do very drastic things to not only the area around the black hole, not only the galaxy that the black hole lives in, but even the large scales of the universe. Yeah.
So, okay, you said they're in the center of galaxies. So is it like they're kind of a drain and everything's kind of slowly rotating toward them?
That is a very common picture that people have in their heads.
Yeah.
But actually, gravitationally speaking, black holes act like any other massive object.
Okay.
You have to be close enough to it to actually get pulled in. So if we were to take the sun in our solar system and replace it with a black hole that's the same mass as the sun, Earth wouldn't get pulled into it.
Oh.
We just keep going around in our same orbit because we're very, very far away from that event horizon.
So they're not all consuming monsters. They're just a fixed point that everything else orbits around.
Yes. They're a big gravitational potential source, but they're not vacuum cleaners. They're not sucking things in from across the expanse of the universe.
Okay, so, but how do black holes get there? They don't start it. They don't just wink into existence as black holes, right?
No. This is a very open question in the field, particularly the big black holes. So there are different masses of black holes that we see, and typically we talk about supermassive black holes and then stellar mass black holes.
Okay.
So stellar mass black holes are the mass of a star, and they form essentially when you have a really big star that reaches the end of its life, becomes gravitationally unstable, and just collapses in on itself, makes a black hole. And so these are, 10 times the mass of the sun. We're seeing them up to maybe 20, 100 times the mass of the sun. But then in the center of pretty much every big galaxy, we see supermassive black holes that are millions, billions of times the mass of the sun. And how you get from something that came from a star to something that is that big is a really big question.
Because they're so much bigger than stars.
And we're seeing them early on in the universe, where if black holes can grow, they can eat material up, they can combine with other black holes, but we see them so early on that there's a question of how could they get so big so quickly? Could they start from something that was actually bigger than just one star? Could you get a direct collapse of a giant cloud of gas that forms into a black hole? Could you get a collapse of a cluster of stars that form into a black hole? So a lot of people are trying to figure this out, but we aren't entirely sure how these supermassive black holes came to be.
Okay. When I was reading through your website and some of your work, one term I kept coming across was galactic feedback. Can you tell me what that means?
Yeah. So that is the idea that, like I mentioned, when you have stuff around a supermassive black hole, there's energy that can go back out into the galaxy.
Okay.
And we call these feedback processes because often they are connected with cycles. So if you think about material around a black hole, it gets really hot. There's a lot of energy that's coming out of it. It can create pressure and push gas away that prevents the black hole from growing. And so you kind of lose that disk of material around the black hole, but now you don't have any more pressure to keep things. And so that material can then come back and then the cycle can start again. So it's these ideas of these feedback loops where things can sort of feed into each other. But really, we mostly use a term when we think about things that put energy back into the galaxy. So material around supermassive black holes is one of those, but stars can do this as well. Supernova, big explosions from stars, winds that are driven by stars. These are other forms of feedback.
Okay, so I think I know what a galaxy is, which is a collection of solar systems. Yes?
Yes. There's... One of the difficult things about astronomy is humans like to put things in boxes.
Sure.
And the universe tends to exist on a spectrum.
Oh, boy.
And so the difficult thing with galaxies is there are some things like the Milky Way, these big spiral arms, we see giant structure, and that's very clearly a galaxy. But there are also small galaxies, we call them dwarf galaxies, that can look a lot like clusters of stars that we find within the Milky Way. So how you define what's just a big cluster of stars versus what is a small galaxy is tricky. Sometimes people talk about the dark matter content, which is a whole other mess.
I don't know if I want to get into that.
Yeah.
Okay.
But it's essentially, For the most part, we think of galaxies as gravitationally bound collections of stars, gas, and dust, and they sit within this halo, this bed of dark matter. When we think about studying galaxies from the perspective of humans and why that should matter to us, when we think about where we came from, all of the materials that exist in this room, those all came from space in one way or another. Most of them came from stars doing fusion, turning smaller elements into bigger elements. Eventually, those elements go back out either through the form of those winds that we were talking about or through supernova, and then that material propagates through the rest of the galaxy and can eventually form new stars and new solar systems.
Okay.
And so we care about these cycles, and we care about the ways in which materials are distributed and how things can form or be destroyed, because that matters for how we can be here.
And when you're talking about these things happening, what time scale are we talking about? Because you're saying, like, there's a lot of stuff going on out there, but
astronomically speaking, right?
Astronomically speaking, yeah.
So, the universe is 13.8 billion years old, which is, I would argue, a timescale that humans cannot comprehend.
No.
I know I cannot. My brain does not work in billions of years.
Yeah.
It doesn't work in millions of years. It barely works in 10 years.
Same.
Right. So I think that the timescale that is of importance for me when we talk about galactic evolution is hundreds of millions to billions of years.
Okay.
Stars can be shorter. The big stars that explode, can live for 10 million years. That's a short lifespan. The sun is going to live for about 10 billion years, and it's sort of the intermediate mass star. So there are stars that live a lot longer, and there are stars that live a lot shorter than that.
Earth is like 4 billion years old.
4.5, yeah.
4.5 billion years old. Yeah. What's 0.5 when we're talking billions? Anyway.
You know what? It matters.
If you say so. 4.5 billion years old, and then you're talking hundreds of millions of years for a galaxy to form and change and do different things. So I guess the question I'm driving at is, how do you observe these things? Because you're certainly not watching it happen in real time.
Yes, that is one of the major issues with astronomy is we do not exist in the timescales where we can watch an individual object evolve from start to finish and see the different cycles it goes through and the way that it changes. We can see a lot of different objects at different stages of their lives and start to put a puzzle together that gives us a complete picture of what's going on in the universe. One of the great things about the universe is that it is a natural time machine.
Okay.
Because light does not travel instantaneously. It takes time to get from one place to another. And when we're talking about something as big as the universe, it takes a lot of time for light to get from a distant galaxy to us. So you'll hear astronomers use words like light years as a measure of distance. So light year is just how far light can travel in 1 year. And when we talk about scales of galaxies, the Milky Way is 100,000 light years across.
Okay.
So it takes 100,000 years for light to get from one side of our galaxy to the other side.
Oof.
And that means even within our own galaxy, we're seeing things as they were in the past significantly. The nearest galaxy to us that's big is called the Andromeda Galaxy, and it is 2 million light years away. So we're seeing it as it was 2 million years ago.
Right.
But that's the closest thing to us. We can push to galaxies that are 10 billion light years away or further, 40 billion light years away, and see them as they were in the past, see them as they were in the early universe so we can understand better what the early universe was like, because we can literally see it.
Does the enormity of that freak you out? Because it freaks me out.
Sometimes.
Okay.
I think it provides a good perspective. I think that that's a big draw of the field to me, is thinking on cosmic scales is a good reminder both of how small we are and insignificant, but also of how much we are a part of this. We're talking about these cycles and ecosystems, and we live in that. We exist because of these processes that have been happening for billions of years. We're a part of this. And so there's a level of comfort in that too for me.
As in, every problem you have is really a small problem, or like...
Every problem we have is a small problem, and it's also quite wonderful that we are able to exist in this universe.
Oh, okay. That is wonderful. I like that. Yeah. Okay, so you can't observe this stuff in real time. How do you figure out, other than looking at snapshots of galaxies at different times, how do you try to put this all together?
So one of the big tools, and the thing that I work with mostly, is simulations.
Yeah.
We simulate the universe. simulations act kind of like an astrophysicist laboratory.
Okay.
Because we can't create the universe in a lab, but we can try to simulate it. And we can create simulations that span the history of the universe so we can actually really see how an individual object can evolve across those timescales.
Okay. When you're talking about simulating the universe, that sounds very computationally intensive to me. You're not running these on your laptop?
No,
Okay.
I run them on NASA's supercomputers,
Whoa.
and they take weeks.
Okay.
Yes.
Okay. And so when we're talking about a simulation of the galaxy, we're talking about models, right? You're modeling things.
Yes.
Okay. So when we say galaxy simulation, can you put that in more practical terms for me? Is that a map? Is it a big image? Is it a theory? Something else? Like how far? Everything?
Sometimes, kind of. There's a lot of different simulations and different types of models. People will simulate individual objects. People run simulations of just black holes and the areas around them. Mm-hmm. I use what we call cosmological simulations.
Okay.
So these are things that are millions of light years across, contain thousands of galaxies in one simulation volume. And what we're trying to do with these is capture all of the main processes that go into galaxy evolution. So that includes modeling things like dark matter, which I know you don't want to talk about. It's just stuff that doesn't interact with light. That's all it is. It's just material that doesn't interact with light.
That sounds way too simple.
That's what it is. We don't know a lot because light is our main tool for studying the universe.
Okay.
And so it's hard to study something that doesn't interact with light. But we can see its gravitational effects. So we know there's something out there, but we just can't see it.
It's stuff that doesn't interact with light, but has gravitational force.
Because it has mass.
Because it has mass.
Yeah. So we include that in our models. We essentially just say there's this dark matter. This is just stuff that interacts gravitationally, nothing else. Then we say there's gas in the universe. And so we need to model the hydrodynamics of how that gas evolves, how it evolves in terms of its temperature, its velocity, its pressure, density. So there are these really complex mathematical equations that are being solved across all of the volume.
Okay.
And then we have things like the astrophysics, star formation. We have to model, when gas gets above a certain density, it can form stars. Black hole formation. If you have a galaxy, oftentimes we just say there's a black hole in the galaxy. We don't model that from first principles because, like I said, we don't really know where they came from.
Right.
Truly, we're just trying to capture as much of the physics as possible. We want to be able to see when galaxies collide, what does that do? When you have feedback that's coming from the supermassive black hole, what does that do? When you have stellar populations that add different chemicals to the gas, what does that do? So we're trying to model all of these things at once, and it's very computationally expensive.
How did you become interested in this field? Like, it's so daunting. Just talking to you about this stuff is like, genuinely, I'm just like, I don't know if I want to keep talking because like I don't get it, man.
I'm glad that you're having so much fun chatting with me. Thanks.
It's so daunting. Like, how did you become interested in this and then gain the foundational knowledge to like keep at it? Because like, I'm still stuck on dark matter, man.
Sorry, I shouldn't have brought it up. That's on me. I first became interested in astronomy when I was like in middle school.
Okay.
And I started reading books by people like Carl Sagan. Mm-hmm. And I think that it was one of the first times in my life where I was like, wow, we really don't have all the answers. Like, there is so much that is still unknown and a mystery. And I was really excited about the prospect of being a part of answering those questions. And I think that astronomy is a field that in the last 100 years has changed so dramatically. And we've seen so much progress and change that it was very easy to get inspired by it and excited about it. The reality of doing research is different. It's up and down. I spend most of my time debugging code and not contemplating the mysteries of the universe, but contemplating why this Python routine won't run. And that's really much more of what the job is.
Right.
But I think that kind of innate curiosity and excitement about space is something that I try to hold on to.
Okay.
Yeah.
Do you have a favorite galaxy? Like, you model the whole cosmos, but like, do you have a pet favorite? Who's your special boy or girl?
I do have a little favorite. One of the things that I work on is analyzing results from this new X-ray telescope called XRISM. It was launched a couple years ago. It's a collaboration between JAXA, the Japanese space agency, and NASA. And so one of the galaxies that XRISM looked at is a galaxy called M82.
Okay.
Which is also known as the cigar galaxy because it kind of looks like a cigar.
Okay. Yeah. All right.
But when you look in different colors of light, so not just the visible light our eyes can see, but lower wavelengths, higher wavelengths of light, you see that there's a cigar and then there's these huge outflows of material that's like so many different temperatures, different phases of gas, really complex structures. And so it's a really interesting case study for these sort of feedback processes, because in this case, these outflows aren't driven by the supermassive black hole. They're driven by a ton of star formation that's happening in that center of the cigar.
Okay.
So you have a bunch of supernova going off, you have a bunch of new stars being born, and it's powering these huge winds. And so that's the one galaxy that I actually study as an individual galaxy.
Okay, so
that's my favorite.
It's your very special one.
Yes. Yes.
Real basic question, borderline stupid. Why is it called M82?
In the 1800s, there was this guy named Charles Messier. He was a French astronomer, and he was really, really interested in comets. So he really wanted to find comets, and he kept looking and seeing these fuzzy things and getting excited because he thought they were comets, and then he would look and they just wouldn't move in the sky night after night. Not a comet. He's like, not a comet. Yeah. And so he made a giant list of not a comet, and each one of them is numbered, and we call them the Messier objects. There's Messier 1, 2, 3, 82.
How many do you find?
150 something.
Good job, French guy.
And I mean, a lot of them are like other galaxies. A lot of them are nebula, star-forming regions, or a star that just died in the Milky Way. There's a lot of different objects. But for some reason, that catalog has just kind of lasted through astronomy. So the M stands for Messier. You'll hear a lot of M82, M13. Like there's a lot of these objects that have a name that is M something, and they're just not a comet, number 82.
What a legacy.
Yeah.
Do you get to name anything? Do you get to name your
I can name my simulations.
Okay.
Yeah. So
the Graysonator?
No.
Oh.
The suite that I've been working on, there's a lot of big kind of simulations that are used by a lot of people out there. And one of the big ones is called Simba, as in like the Lion King.
Simba.
Exactly. And I have built a new suite of simulations that plays around with the physics in Simba. And I named it Rafiki, which is like the baboon. And I actually came up with an acronym for it that I was really proud of.
Did you start with Rafiki and work your way backwards?
We call it a backronym.
Oh, yeah, that's exactly what it is. I mean, scientists love to do that.
And astronomy is full of terrible names and terrible acronyms. Okay. But Rafiki kind of makes sense within, like, it's refining AGN feedback in kinetic implementations, which I'm sure sounds like gibberish to you.
Those are all words.
It does kind of relate to what I'm doing in the simulation suite, which I'm very proud of.
I mean, well, Rafiki's good. I like that. It's good companion to Simba.
Exactly.
If you enjoy conversations that spark curiosity and make science easy to explore, check out Ask a Biologist, another podcast from Arizona State University. Hosted by Charles Koselik, aka Dr. Biology, each episode invites listeners into the wonders of the natural world, from animal behavior and the human body to the big questions that scientists are asking about life on Earth, in a way that is engaging, accessible, and fun for curious minds of all ages. Discover new episodes and explore hundreds of science stories, activities, and resources at askabiologist.asu.edu and wherever you get your podcasts. I want to jump back to something because I'm still not totally sure if I understand what you're actually getting from the simulation, like what the output is. Is it an image? Is it a bunch of things that say black hole did this thing?
It's closer to that second thing.
Okay.
So in the simulation, we have a bunch of what we call particles. So there are black hole particles, there are star particles, there's dark matter particles, there's gas particles, and there are trillions of these. And each particle, we get an output that says, here's the particle, here's where it is, here's how quickly it's moving, here's its temperature, its pressure, its mass. And so it's essentially just a list of the different particles in the simulation.
It lists trillions of lines long.
And different types of things and different information. You know, some of these were tracing how much hydrogen is in this particle versus carbon versus oxygen versus, there's so much information.
So is it just like a crazy spreadsheet?
Essentially, yes. We don't store it in Excel because Excel would break, but it is pretty much that. So there's a lot of tools that can take that information and create actual scientific products out of that. So we can make images. We can say, just create a map of where all the dark matter is, and then you can see that. We can say, well, here's all the gas. We know its temperature and its density. That can tell us about what sort of X-ray light it would emit. And so we can create a mock image if we were to look at this with an X-ray telescope.
Okay.
And so that's kind of the stuff that I do, where I create these mock images, these mock data products, and then compare it to what we see with actual X-ray telescopes.
So there's a degree of artistry to what you're doing in an interesting way.
Yeah, there's definitely, I think, a lot of connection between science and art. Mm-hmm. I think you see it a lot more in telescope data analysis. When you look at the beautiful images that come from big telescopes like Hubble and James Webb, we are assigning colors to the light. When we get an image from a telescope, it's black and white. It's, do we see light or not? Mm-hmm. And so when we take images in a lot of different wavelengths of light, you can turn it into a picture, but you kind of have some artistic freedom in terms of what colors are you assigning to different wavelengths and how are you layering these things together. And so it's very much a creative, artistic side of the field.
This is a random one. Is there something very contentious that astrophysicists argue about?
Oh, yes. Oh, my goodness.
What's your favorite astrophysicist slap fight?
Yeah, there's a lot of beef in science.
Yeah.
And it's kind of silly because it's a very, very small number of people who care about it.
Well,
but they care very, very deeply. One of the big ones is the universe is expanding. Galaxies are moving away from each other at a faster and faster rate. But depending on how you measure that, you get different numbers. And the error bars on those numbers don't overlap, and they're getting smaller and smaller and continuing to not overlap. So that's one of the biggest, we call it the Hubble tension. The biggest tension in astronomy is, why are the error bars not overlapping? Who's doing something wrong? Are we wrong about something very fundamental, or is someone just not taking into account some process in their data analysis? So that is one that I have seen people get actively heated about in public, in conferences, on stage. And I think that that's one that could hopefully potentially be resolved within the next 5 to 10 years as we get more data.
Cool. Where do you come down on that then?
I come down on science is hard, and I don't think we should be too attached emotionally to our results. And I think that following the data and being like, right now, with all the information we have, these are the best error bars and the best fits that we can create. And they're different, and that's really interesting and worth exploring why, but not worth telling other people that they're doing something wrong over, unless there is actually an error that you can find, which no one has found.
Boo. That's too diplomatic. I want you to throw someone under the bus.
You know, I don't think that that's a very good idea, as I am just starting out my career.
Okay, good point.
Want to keep those options open.
I will start fights with astronomers for you.
Perfect.
Because we are anti-astronomer on this show.
Great, thanks.
She's not going to comment on that one.
Nope.
And until I have an astronomer on the show, in which case I will be anti-astrophysicist.
I like it.
And I will throw you under the bus.
And
sorry.
You know what? That's fair.
Okay.
Yeah.
You described people getting very heated about the Hubble tension, right? Very important to those people. However, I would go out on a limb and say astrophysics and astronomy does not really affect daily lives. But why do you think this kind of research is still really important?
Yeah.
Because, I mean, from talking to you, you do think that.
I do. I value it, and I think that it is valuable. And I think that there are a lot of different reasons why. The first is that when you talk about astrophysics as a whole field, it's very, very broad. Mm-hmm. The sort of thing I do, black holes and distant galaxies, very hard to find the direct relation to. But there are a lot of astrophysicists who study things like the solar cycle and solar activity, solar flares, coronal mass ejections, that pose a threat to Earth. Mm-hmm. Things like hunting for near-Earth objects, potentially dangerous asteroids. Very obviously important to pay attention to those things, and that is within the field of astronomy. I think that there is a lot of technological growth that comes from astronomy, particularly when you think about instrumentation and developing new fancy telescopes with these very complex, sophisticated optics that can have really great applications in a whole bunch of different things. We see it in the medical field, we see it in security, we see it all over the place. Similarly, we were talking about big data, and I think that there is a lot of great research being done on just how to manage big data in astronomy that is very useful for anything else that deals with big data.
Right.
Which is a lot of fields right now.
Yes.
I think another benefit of it is you don't necessarily know when things are going to become important down the line. An example of this that I really like is relativity. So this idea that time behaves differently depending on where you're at or how fast you're moving was kind of developed by Einstein and very theoretical. You know, we're not necessarily going to be able to see this. But actually, if we didn't know about that, GPS satellites wouldn't work. In order for our GPS satellites to actually function, they have to account for the relativistic change that's happening because they're going so quickly around the Earth and because they're experiencing a different gravitational pull than we are here on the surface.
Okay.
So the clocks on GPS satellites are having to be constantly updated to account for this sort of weird general relativity, special relativity, physics stuff in order to actually function as GPS satellites. It's an example of how a very strange, out there, weird topic can have practical effects that you wouldn't think about or you don't know are coming down the line for humanity.
The theory of relativity means I don't get lost in my car.
Exactly.
Cool.
Yeah.
All right.
And I think the final thing and the thing that drives me mostly is astronomy and astrophysics is one of the more philosophical of sciences. It's really trying to answer the biggest questions, like why are we here? How did we come to be here? What is in our future? And I think that there is a lot of benefit to considering those questions and not minimizing them compared to some of the more practical things. I think that there's a reason humanity has always asked those questions and has always been driven to understand our place. And it's important to foster that curiosity. And in fostering that curiosity, we see the ways in which astronomy brings people together. It's a very, very popular science. People love learning about astronomy. People think space is really cool.
It is.
And that both unites people. We see huge international collaboration, even just in the ISS, on levels that we don't see in most other fields. And we also see it being a main driver to get people into scientific fields beyond just astronomy. So we see like Astronomy 101, a gen ed course, that's one of the most popular science courses that people take in college. And it's also often the last science course that people take in their entire life. And so there's a huge opportunity to help with science literacy, help build trust in science, help get people excited about science that comes from caring about astronomy and fostering the field.
Now I want to talk about science communication.
Yeah.
You've built an online presence explaining astronomy and I guess astrophysics too, right?
It's all, yes. Truly, you can use them interchangeably.
Great.
It's okay. Yes.
You've built an online presence explaining space stuff.
Space, yeah.
What made you want to start doing that in the first place?
I started my first year of grad school, and coming into grad school was a very difficult time for me, frankly. Like, it's a weird transition because being a grad student is not really like being a student. You'll take a couple of classes in your first couple of years, but most of what you're doing is research. And it's a very weird transition to go from being a full-time student to being someone who is also technically a student, but is expected to do research. And you're starting all that off. And it was a time. And it was a time where I felt like I was losing sight of why I was doing this in the first place. The life really became about the debugging Python and less about I'm studying astrophysics.
Yeah.
And so a lot of it for me was a way to reconnect with my excitement, to talk about just sort of the more fundamental surface level things that got me interested in the field in the first place, build that energy back up, help people find that energy too. And it was a creative outlet. It's fun to make videos. It's nice to do something that's not just research.
When it comes to science communication, what is harder for you? Learning the science or like actually explaining it clearly to people who aren't specialists? Because different challenges, but they both seem very difficult to me.
I think that one of the more difficult things has been trying to figure out like what my goals are with the stuff I do online. How much of it is the selfish trying to reconnect with the field, which is a part of it. How much of it is about trying to inspire other people to be scientists? How much is it about being open and kind of pulling back the curtain on the process of being a scientist, because that's something I had no idea about going into grad school. I didn't know how much coding was involved. And so showing people what it's like, how much of it is about correcting misinformation online and sort of playing that role, how much of it is just teaching and trying to get concepts out there. And that was a bigger challenge for me, is trying to figure out how to balance that and sort of really be intentional about the videos I make and why I'm doing this. But for the most part, the developing explanations was not too challenging, because I was coming out of undergrad where these things were being explained to me constantly. And so I had seen it been done, and it was just a matter of sort of repackaging it into this social media format.
Okay. So a moment ago, you mentioned correcting disinformation online. So I'm kind of curious, are there some common misconceptions you've encountered regarding your field? I would think that there's not even enough like general knowledge out there for there to be misconceptions. You're talking about dark matter, and it's like no normal person knows what that means. I'm sorry. I still don't know what it means. I'm stuck on dark matter.
I know. I have so many regrets about bringing it up.
Oh, you should.
It's going to be okay. The main things tend to be aliens.
Oh, okay.
That's not my research focus. I have a lot of friends who do exoplanet science. I communicate with a lot of people who do that. There are a lot of flashy headlines that come out about biosignatures being detected, or alien material
unknown
being discovered,
signals,
or this interstellar object is an alien spacecraft. And that's a lot of the stuff that's pretty easy to kind of combat. Honestly, the black holes being vacuum cleaners, that's a battle that I'm constantly fighting. We're not being sucked into the black hole in the center of our galaxy. Okay. That's something that a lot of people kind of visualize. Yeah. There's some stuff that is more like fun like that, and some stuff where it's actively frustrating and kind of dangerous because people are getting the wrong idea of like how science works and what we're actually finding versus not.
Do you think that scientists have a responsibility to communicate? And can you tell me more about that?
When you go into a scientific field, you are trained to do research, number one. Mm-hmm. You are not often trained to teach. You are not often trained to communicate. And when you are, it's normally communicating to other scientists. At the same time, especially in a field like astrophysics, a majority of our research is funded by public money. And a majority of what comes out of that public funding is peer-reviewed scientific papers that nobody can read, even if you're in the field sometimes. And I think that as a system is broken. I think that erodes people's trust in science. I think that it leads to a lot of people not understanding why things are worth funding in the first place. And I think that it is a very easy system for things like misinformation to happen, because there's not a lot of good information that is accessible and understandable by the public that can kind of counteract that. So I think that scientists do have a responsibility to communicate their work with the public and in a way that is interesting and engaging and fun and correct. I also recognize that is incredibly difficult to do, and scientists are not trained to do it. Yeah. And so I think that there's a lot of opportunity for people who are trained to do that, to bring public awareness to, honestly, like you're doing here, try to have conversations with experts, but at a level that people can understand, not necessarily having to come from the scientist on their own, but being helped by people who do have a background in journalism or communication.
I was curious if there's any fiction out there that gets more right than it gets wrong about astrophysics, or if you just have some like favorite movies that involve like a black hole or something.
Well, I have two issues.
Oh, okay.
Not with that question, personal issues.
Sure.
The first is I'm scared of space. I'm an astrophysicist. I understand that's ironic. I am not an astronaut. I have no interest in going to space. Yeah. Space movies freak me out. Really? Like watching Interstellar, I was like cowering. It's something about not being able to breathe. So I don't watch a lot of space media. Really? Interesting. I think that the other issue is like, I also don't read a lot of sort of popular science books because it is my job. People often ask me for book recommendations, and I'm like, I do research all day, and then I come home and I make a video about astronomy, and then I am not about to pick up a book about astronomy too. Like, I need to do something else my life is not just science. And so I don't read a lot of science books because, yeah, it's just too much for me. There are good ones out there. One I have read in the last 5 years that I would recommend it's called The End of Everything by Katie Mack, and it's about how the universe is going to end. And she throws out different possibilities, and it's a very fun read.
Okay, well, that leads me into my last question. Do you have, if anyone wants to learn more about astrophysics or just kind of get a primer on black holes or stellar feedback or anything like dark matter? Well, no. I reject you mentioning dark matter one more time. If someone wants to learn more about astrophysics, what are some things you would recommend other than The End of Everything? And it doesn't have to be just astrophysics. It could be something that inspired you recently or, you think is worthwhile that took your mind off of debugging code.
Well, I am going to plug myself, which is embarrassing. But I do truly think that myself and other scientists who do social media content do really cool things. So I'm Space According to Skylar on Instagram and TikTok and YouTube, and you can find all my stuff there. And I think that it's a fun way to just get little bite-sized pieces of science throughout your day. There are really good science writers out there. One in particular, a blog called Starts with a Bang by Ethan Siegel. It does a really great job of breaking down astronomy concepts and like recent space news. And so I would also recommend that.
I'll put all your socials in the show notes as well as Starts with a Bang and The End of Everything. Skylar, thank you so much for coming on the show. Dark matter discussion aside, I really enjoyed this.
This was great. Thank you for having me.
Thanks for tuning in. If you enjoyed the show, please leave us a 5-star review on the podcast app of your choice. If you found us on YouTube, we'd appreciate a like and a subscribe. Lab Coat Optional is brought to you by the talented people at the Knowledge Enterprise Strategic Marketing and Communications team. Knowledge Enterprise is led by Executive Vice President Sally C. Morton. Remember, lab coats are optional on this show. We want to keep our researchers safe in the lab, so wear your PPE. Until next time, stay curious.